Okay, so we're going to finish up chapter 12 today. I'll go through a little bit with you, and then you guys can take a look at the key to see the rest of it here. So typically when fishing tournaments occur, they measure fish by the length instead of their weight, because weighing a fish that's flopping around, might not be very accurate before throwing them back in the water. What you've been asked to do is to come up with a way to convert the length of the fish to its weight. You contact a nearby marine research laboratory and they provide reference data on the length and the weight for Atlantic Ocean rockfish for several sizes, along with the scatter plot of the data. So here is our data. There is your scatter plot there on the right, and obviously that's not linear. Now if I were to draw a line through there, the line of best fit, there'd definitely be a pattern in those residuals. So why do you think graphing weight versus length is not linear? Why does it look like it might be a little exponential or a different form like that? That is because, if you think about this, weight is three-dimensional. And your height, or in this case, your length, is 1. So that's why we end up with something of that nature there. So how can we transform this data so we can produce a graph that is in fact linear? Well, we can think about how about we get these onto the same dimensions. Like maybe I could do weight versus length to the third. Cube my length. Now they're both technically kind of in 3 dimensions. Or another way to do it, I could take the cube root of the weight versus the length. So 2 different ways that you could approach that problem. Now, the whole point of this chapter 12.2 is to take roots or natural logs or square your variables to create a linear model that is appropriate. Okay, so instead of doing length versus weight, we could be looking at length versus the cube root of weight. And that pattern might help us be able to figure out the predicted weight. Okay, so checking out these 2 graphs here. Okay, now that we have a linear relationships to examine, here are the residual plots. Okay, so this one over here was our first method of doing length to the third, and that's the residual plot that came out. And as you can tell, it just kind of jumps back and forth. We do have this one that kind of gets way out there, but again, it is a random scatter. Same thing with this one, which is length versus the cube of the weight. Again, has pretty much a random scatter there. The variance might get a little bit larger at the end, but there is no clear pattern, so that means it's appropriate. So given the equation of the least squares regression line, but before we do that, let's define some variables. So in this case, we would have x is the length in centimeters. Y would be the weight. So again, centimeters and grams. So for transformation 1, your equation would be y hat is equal to, so we got constant 4.066 at plus 0.014 or 15, we'll just round it. And now it's not x here, it's x cubed. And then for transformation 2, we're not predicting y, we're predicting the cube root of y, which would be equal to a negative 0.022 plus 0.25 x. Okay, now if you do any calculations for the AP test using an output like this, make sure you do use those full numbers, but you are fine to write them in the way I just did there. Suppose a contestant is fishing in the fishing tournament, catches a rockfish that is 36 centimeters long. Use this model to predict the fish's weight. So for the first one, it's pretty easy. Okay. Y hat equals 4.066 plus 0.015 times 36 cubed. Okay, we go and do that. We end up getting 703.906 grams. So that's pretty straightforward there. But if we look for number 2, we're predicting the cube root of y. So negative 0.022 plus 2.247 or 25 times 36 gives me 8.87. But remember, that's the cube root. So that would make that y hat would actually equal that cubed, which would give us 697.869 grams. So both of those are pretty close to each other. So it does work out pretty well, either method. And then interpret your S. Okay, so first S here. Okay, remember S is the average error that you have using your equation. So for number 1, the average error when predicting, or average error using least squares regression line from using length cubed is 18.84 grams. So if using the least squares regression equation that we used or made up there to predict the weight from length cubed is 18.84. So again, make sure you look at my key. I write a little bit better of an answer there. I write the average error when predicting rockfish weight from length cubed is 18.4 grams, or about. I'll write that out in the second one here. So for number 2, a more formal way of writing this, the average error when predicting rockfish, actually in this case, the cube root of the rockfish's weight from length is about 0.124 grams to the 1/3. Or you could write cube root grams, whichever way you want. All right, next problem here. A student opened a bag of M&Ms, dumped them out, and ate all the ones with the M facing up. When finished, he repeated that same process all over. Okay. And I do this activity a lot with kids, and you notice it's not linear right away. Sometimes I'll do, you start with an M&M. If it lands at M with M up, you add another M&M. So you drop 2. If both are M's, you add 2 more, and you eventually see that exponential graph that occurs from that. So here's the table they ended up with. After course 1, there was 30. Then on course 2, down to 13, then down to 10, 3, 2, 1. So obviously not a linear pattern there. So the whole point of this chapter, again, is to try to linearize or do a linearization of this so we can have a linear model that would help us predict the outcome. Since the number of M&Ms should be cut in half after each course, an exponential model should describe the relationship between the variables. A scatter plot, the natural log of the M&Ms remaining versus the number of course number is shown below. The last observation in the table is not included. Why is it left out? Okay. Well, in the last one, it's left out because if we were trying to take the natural log, the ln of 0, yeah, that's going to be undefined, and we're not going to be able to do that there. Okay. This is not actually on the graph or on the table here, but if we're going to make this and it'd be x versus the ln of y, we'd get something that is pretty linear there. Okay, to do that, you would want to put the course in L1, M&Ms in L2, and then in L3, do the ln of L2, and it'll take all those values for you there and create us a new graph. Okay, so then in this case, x is your course number, and y is the number of M&Ms. Okay, so this is now something we can predict the number of M&Ms going to be left by using a linear regression model of x versus the ln of y. Explain why it would be reasonable to use an exponential model to describe the relationship between the number of M&Ms remaining and the course number. Why is it reasonable? Because the scatter plot of ln y versus x shows a strong negative linear relationship. Okay, so this is, again, a really good review for us for Chapter 3 as well. We look at the scatter plot, strong negative linear relationship. That's how we describe those. Okay, so that's why it's appropriate. Now, we would want to check residuals. To make sure that everything is A-okay and good for us to move on. Okay, next part. Give the equation of the least squares regression line using that chart over there. So I want you to pause the video, give it a try real quick, and then when you're ready to, and then you have it, let's play the video again. Okay. So again, we know it's the ln of y that we're predicting, okay, which would then equal 4.0593 minus 0.68x. Okay, so once we plug in our x value, and then we'd have to eat up to figure out what y would actually be. You could actually go change this to get y by itself if you wanted to. Okay, but we don't have to worry about that in this case right here. And then finally here, looking at the residual plot, what do we know about the appropriateness of this? You know, there's not many points. We're above, below, above, below, above, above. So in my eyes, there's no pattern in the residuals. A linear model is appropriate. But again, it looks like it's probably more appropriate near the ends. You know, that in the middle we're kind of far off there, but again, it's still an appropriate model. So let's have you go ahead and try the next page. I'll create another video that you can come back and look at for those parts, and you can always ask me some more questions. And that pretty much does it for